Welcome to the second lecture on Matroids. So last time we set up the definition, a kind of definition intuitively taken from the directed k-path algorithm. But before we go, so this is the two Bollobas family of lemmas we were talking about last time. So you are given an universe and the pair of sets ai bi with the property that ai intersection bj is equal to empty if and only if I equal to j, then the number of such pairs that we can obtain is p plus q choose p. And the plan was that we will give a proof of this lemma, and so I will see how we can derive what do you call the cardinality f hat, which is same, how to compute this and then show its usability. Okay. So now let us just boil down to proof of this lemma. Okay. So let us prove this lemma first. Okay. So here is a proof. Okay. Let us consider a random permutation okay. Consider a random permutation sigma of u, okay. And for every I in M, okay. So two lemmas we would like to prove. So this defined for every I, ei be the event that each element of ai appears before bi sigma. Okay. So this is going to be my event. I will explain to you. So we are going to prove two lemma or two observation. Observation 1 is that ei and ej are disjoint events. Ei and ej are disjoint events. Okay. Of course, I is not equal to j. And observation 2 is probability of ei, that event ei happened, is equal to 1 over p plus q choose p. Okay. So now let us try to see what is the random experiment happens. So we choose a random permutation row of u, meaning there are n factorial permutation of u. You chose one permutation row. Okay. So you chose row with probability 1 over n factorial. And what is my event? So event is, look at this permutation row. Now it means now you mark the elements of ai, these are the elements of ai, and we say that look at, so suppose the red crosses are element of say ai, okay, and let us suppose the green crosses are going to be elements of bi. So I am going to call that, what is an event? If all the red crosses, meaning you mark all the vertices which are from ai as red and all the red crosses appear before green crosses, then that is your event ai. Okay. If green crosses if there is any red cross after some green cross, then that is not a correct event. So now you ask yourself, what is the probability of happening of row? Okay. So what you do first? Okay. Okay. So first, okay. So now let us try to understand how many permutations are there. Okay. So what is the probability of the event ai? So probability of ei is number of permutations in which elements of ai appear before bi divided by n factorial. Okay. Now so how do we do this? So first of all, you choose the places of ai and bi. Okay. How many such places are there? See, from this you choose p plus q. So you have chosen. So first you have chosen, and you know, right? And on the remaining, you know that on the remaining, like, or on these places, p plus the elements of, so you chose some. So you know that these are allocated for elements of ai and bi, and on the remaining, any element of my universe can come. So that is n minus p plus q factorial. And now look at the places where I know that the out of this p plus q places, first p places are given for ai and the next q places are given for bi, but how these elements are permuted among themselves, it does not matter to us. So this is p factorial and q factorial. Okay. So this is how you can choose, you can have a number. So these are the number of permutation which elements of ai appear before bi. You choose the places where ai and bi will occur, that is p plus q. You know the first places are taken by ai and the last places are taken by bi. So, and how they are permuted among themselves does not matter. So p factorial and q factorial, and in the remaining places any of the elements can occur, any permutation of the remaining elements can occur, which is n minus p plus q factorial. Okay. So now let us do this computation. So what are we going to get? N choose p plus q, p factorial, q factorial, n minus p plus q factorial divided by n factorial. Okay. So if you do some amount of computation, which I am not very great at, but I could try, n factorial from here, this is n minus p plus q factorial, and p plus q factorial times p factorial times q factorial times n minus p plus q factorial divided by n factorial. So this and this term will get cancelled, this term and this term will get cancelled, and what you are left with is precisely p factorial q factorial by p plus q factorial, which is nothing but 1 by p plus q choose, right? That is it. Check. So this is it. So first thing is, so we first proved observation 2. Now observation is say that ei and e are disjoint event. Okay. What does it mean by this? What is the meaning of this? That let sigma be a permutation, then it is part of only this is part of at most one event. Okay. Then this is part of at most one event. Okay. Now let us look at this. Why? Okay. So what you know? So let's suppose you fix a row. Okay. And suppose we had suppose you know this is event ei. So suppose, right. Now what is the meaning of this? That all the red crosses of ai occurs here, and all the green crosses. Okay. So these are element of ai and these are element of bi. Now let us look at any other, suppose for a contradiction, assume that sigma is also part of some aj. Now let us try to understand where will my, let us draw them by brown. Okay. Okay. So this is the law, what you know about aj. You also know that if sigma is in aj, then all the elements of aj occurs all the elements of bj. Now let's look at the last element here. Where can it be? Okay. 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 So let's call this element brown. Okay, this element. If this element, can this element occur here? Because if this element occur after this last red cross chi, then what happens? All the other elements of bj are going to be here, right? All the elements of this guy is going to be here. If the last element of aj is either occurs after the last red or it does not, we will see. But if it occurs at the last of this, right, or the last element of this, okay, then what happens is that look at all the elements of brown, they or all the elements of bj, they also occur after this, which implies that the red crosses and brown crosses, like this and these elements, if this will happen, then that will imply that ai intersection bj is equal to empty, but that cannot happen. Okay. So you know that last element of aj cannot occur after this. So it should occur somewhere before. Okay. Okay. So, but imagine, so this is like, here it is. So this is my last red cross, and suppose my brown cross occurs here, right? Let's say somewhere here. Okay. So this is an element of aj. But if this happens, then what is an intersection of? If this happens, that will imply that aj intersection bi is empty. So if the brown cross occurs after the last red cross, then we can say that ai intersection bj is empty. But if aj occurs before the class, then we can say aj intersection bi is empty. But in both cases we get a contradiction, which implies, this implies that events ei and ej are disjoint. Now why are we interested in it? So look at this. Okay. Probability of ei summation I going from 1 to m, okay, is at most 1, right, and this is equal to m times p plus q choose p, right. So what does this implies? This implies that number of such sets are upper bounded by p plus q choose p, and hooray, that's it. Okay. So the first thing we have been able to show, okay, first thing we have been able to show is that we have been able to prove this lemma, right, which tells us that the number of such sets are this. Okay. Now let us, so given this, let us try to phrase everything properly and define this notion of Q representative family. Okay. What is a Q representative? Okay. Given a universe U, a family F of subsets of U of size B, okay, okay, and an integer q, okay, a set f hat, okay, okay, is called Q representative of f, is called Q representative of f if, what is the property? F hat is a Q representative of f, okay. If, okay, so we already defined the notion of Q representative is basically if for all B subset of U, okay, or rather, okay, if for all B subset of U, if there exists an A in F such that A intersection B is phi implies there exists A prime in F hat such that A prime intersection B is phi. Okay. So, I am going to call a Q representative if it is like if it respects disjointness with respect to all Q side set, in the sense that if I give you a B and you have a set, some set A in F such that B and A are disjoint and B has size Q, then you have to guarantee that such a set exists in F hat. Okay. Okay. And what did we just now prove? So, this is like another lemma that we just now showed. Okay. Let U be a universe, F be a family of subsets of U of size B and Q be an integer. Okay. Then there exists a F hat Q representative of F of size P plus Q, which is P. Okay. And the proof is now simple. Okay. What is the proof? We already have defined the notion of minimality. Let F hat subset of F be a minimal set. Now, if it is a minimal subset, what you know, okay, and let F hat be A1, A2, Am. Now, since F hat is a minimal, you will be able to find for each Ay B1 which intersects with every other A2. So, basically, okay, then you are able, why they are minimal? Because there exists Bi with this property such that, what is the property? That A1 intersects with every other Bm, A2 intersects with every A2 intersects, right. Then, okay, then we have, which implies we have two families AI Bi, I going from 1 to m, such that AI intersection Bj equal to MT if and only if I equal to 0 j. Now, what does that imply by two families theorem? This implies M is P plus Q, choose P. So, now we have been able to show, okay. So, let us go back and let us trace, okay. So, we introduced this notion of like how, if you are trying to understand or trying to construct a directed path algorithm, for example, then if you look at the family of partial sets, which could be like, these are like those sets which like contains a path from U to V of certain length, okay. And basically you can think of these are like prefixes of the path of length k that we are trying to construct, okay. And we said, look, that is too many, and but we said, look, why do we need to keep all this? Let's try to keep only those sets that are important that so what is an important? That look, this set is important because there is some set which it is disjoint with, and no other set that I have kept in the family can be disjoint with this. Otherwise, if for every set that this guy is disjoint with, someone else is already disjoint with in my family, then this set is useless for me. I could have thrown it out. Okay, so that is because of this that we got to the notion of what I call Q representative family. Okay, and the heart of the Q representative family was this two families theorem. Okay, that basically you are given a universe AI BI and the properties, then the number of such sets that we could have is upper bounded by P plus Q, choose P. Okay, and then we just now saw the proof for this, that yeah, this is true, and then we connected it, then we defined the notion of represent. This is the most important definition. So, what is that? You are given a universe, you are given a family of some set size P, and you would like to compute a some set F hat subset of this. What is the property? That with respect to every set of size Q, if F had something like, it satisfies what I call disjointness property, meaning if you give me a some set B of size K, so that you can find me a set A in my family, so that A intersection B is phi, then I should be able to give you A prime in the set which I have kept, so that A prime intersection B is phi. Okay. So before we go about computational aspect of computing Q representative family, let us make a remark. So what is the remark? Okay. Is two families theorem tight? Okay, and the answer is yes, because you take universe equal to 1 to P plus Q, okay, and let us take family equal to all subsets of size P. Then notice that all subsets of size P, right, all subsets of size P, then right, then for every x in F, or rather every AI in F, you take B equal to U minus AI. So definitely AI and BI are disjoint, and because of the cardinality constraint P plus Q, every other thing will intersect with it. So this shows that, and since cardinality of F is P plus Q choose P, right, we can pair them up. So not only this is tight, it also implies that in some sense representative family size is also tight. Okay, okay, okay. So such an object exists. Okay. Okay. So this was existential. Now let us look at the computational lemma. This is computation. Okay. So let U be an universe, F be a family of subsets of U of size P and Q and B. Then there exists. Okay. So I would like to say further, F hat can be computed in time. Okay, let's see. Okay, we will see. Okay. So, okay, we will see. I think as a okay, okay. So let's try to give a proof for this. So I'm going to design an algorithm which will do this job for us. So algorithm is very simple. Okay. Okay. So the algorithm is very simple. It is a it is an algorithm that goes over each set in F, and if it is redundant, then it removes it. Okay. So, this is an algorithm. So, what is this algorithm? It goes over each set in F, and if it is redundant, then it removes. And so, what are we trying to achieve? We are trying to get an F which is minimal. Okay. So, let us ask ourselves, so when do we need AI, or when do, okay, or rather let us say, or okay, when do we need AI, or rather when is AI essential? It is not redundant, okay, not redundant. Okay. So, we already have seen that what is the definition of AI. Okay, let's. So, here it is AI, it is necessary because there exists a set Bi such that AI intersection Bi is phi, and Bi, so this should be Q, not P. Okay. AI intersection Bi is phi, and Bi intersects with each set but AI. This is how we define the minimality. Okay. So, a set AI is essential if I can find a set Bi. What is the property of that? Such that AI intersection Bi is empty and Bi intersects with each set but AI. Only then a set AI, because that is how we defined this. How can we, okay, so this is our computation. How do we check? How do we check if AI is essential? Okay. How do we check if AI is essential? So, what we are going to do, okay, reduce this to a de-hitting set problem. Okay. Okay. How? So, let us, you are given a particular family F, okay, and AI is in F. So, now I am going to say, look, what is the meaning of this AI is essential? Okay. There exists a Bi, okay. There exists a Bi such that AI intersection Bi is phi and Bi intersects with each set but AI. Bi intersects with, okay. So, now what is the de-hitting set or whatever the instance we are going to make, you will see here. So, my instance is, I am going to take an universe, okay. First of all, from here I remove AI, right, because you are not allowed to pick a set, because the set which you want to pick. So, okay. So, what I am going to say, construct Bi as a de-hitting set of some family. Okay. So, what is my family? So, my universe is U minus AI because Bi has to be disjoint from AI, and the family which I create is family. First of all, from family which I create, okay, F tilde is nothing but A minus AI A in my family. Okay, that is it. And of course, remove empty set. Okay, there is nothing to hit. This is it. Now, and fix your parameter K is Q. Okay, D is P, K is Q, And if you do a branching, what is a branching algorithm, right? You pick up a set, you know that you have to pick one of the element here. So it's a very simple branching algorithm, right? You pick up a p size set and you branch in p base. And since you are looking for a solution of size q, the branching depth of this algorithm is depth is bounded by q. So the running time of this algorithm is actually p to the power q, right? P to the power q and right something, okay, some family too, because you have to check whether and take care of. So basically, we're looking. So what is BI? If you have a BI, if you have a set of size q, okay, if you find a set of size q, okay, of course we have to assume that, okay, okay, else, okay. So now what can happen? You found a set u, okay, here you found, okay, if you found a hitting set, right, if you found a hitting set of size at most q for f tilde, okay, now you add, if it could be of size at most q, so add some redundant, okay, okay, let b be a hitting set, okay, let b be a hitting set of our instance, then add some element from, let's call it u tilde, from u tilde to b to make it of size q, okay, and we have such elements because AI had size p, so even if you delete it, B universe has size q, okay. Now let B be a hitting set of 1, add some element of, so now what you know about this, what you know then you have found for this AI a B such that AI intersection B is empty and B intersects with all aj j not equal to I, okay. Then what you know? Then you know such an AI is essential, okay. So you keep such an I. Then we know that AI is essential, okay. Then we know that AI is essential, so we keep it, okay. However, if we can't find desired B, what does it imply? This implies that AI is redundant, so we throw it, okay. And notice that even after you throw it, the B which was guaranteeing that AI is disjoint from this B and B intersects everybody else, that still holds, okay. Okay, so at the end of this algorithm, we are guaranteed that we have an f hat subset of f with the following property. For each AI, there exists a BI of size q such that AI intersection Bj is not equal to empty if and only if AI, if and only if I equal to j. And now by two families theorem, okay, what are we guaranteed? guaranteed that, okay, we are guaranteed that okay. So notice that we have found a family of optimum size, but the running time is far from optimal, okay, in the sense that the running time of our algorithm is p to the power q, okay. Okay, this is the running time, okay. But some observations are in order. For q equal to order 1, this is polynomial time algorithm. This is the first observation to make. Okay. So when you are computing or trying to compute a representative with respect to like only constant size set from outside, then actually you can get some okay, yeah, right. And whatever the size of f hat in this case will also be polynomial in P. Okay, that is another thing to worry about or to note. Okay, so let's see how much we planned. What else did we plan to do now? Okay, so we saw the bound on f hat, computation of f hat. Now we have to show how we could use these bounds and these algorithms to design algorithm. Okay. So what is the running time of this algorithm? It says, look, if you give me a family, then I can take running time polynomial in f and p to the power q to give you the set. But like imagine, as we told, okay, so now let's go back to applications. Okay, people do applications now. Okay, so imagine what does this algorithm tells us. Algorithm tells us that, look, if you give me input and f, okay, over universe u of sets of size p and give me an integer q, I will output an f hat subset of f of size at most p plus q choose p, but the running time of this algorithm is okay. So first of all, I mean, what benefit are we going to get from this algorithm? It says fine, if you give me, so for example, for directed k path, what are we saying? We say, look at STK, if you give me this, okay, we can check if this is, we can compute its representative, or rather let us say okay. Okay, we can compute if you give us this, we can compute, okay, okay, let us say q e, we can compute this, but in time how much? UBP size of this at least this much. Now, we know that this size could be as bad as n to the power big O of k. So, like this computation as such is going to take n to the power big O of p time, right. So, we are, if I give you this itself explicit, then what is the point of, I mean, this computation overall? So, this does not make much sense in that regard. Okay. We will see how dynamic programming can be applied in a very clean fashion, that we will never have this whole set, but we still have a good enough set that if we compute representative with respect to that, we are still good. Okay. And for that, the one property of this representative sets that are useful is following transitivity property. Transitivity property. Okay. Okay. So, what is that? So, suppose you are given a family, okay, of over U, okay, each set in F has size p are given and you are given an integer key. Okay. What I want to say is that, look, suppose we have F prime, which is say Q representative of F, and F tilde is Q representative of F prime. This implies that F tilde is Q representative of F. So, this is what I mean by transitivity. Okay. And this is very easy to prove. Okay. Okay. So, what is the first meaning of this F prime, right? We know that, okay, rather yeah, this is fine. Okay. So, now you suppose you have a set, you gave me a set, let us say P, okay, such that, and such that say there exists A in F, of course, okay, it's fine. Okay, that's given. That's first. Now, because of the first representative implies, this implies there exists A prime, there exists A prime in F prime such that A prime intersection B is phi. This is second. Okay. Now, F hat is a representative. So, now given that B and now you apply at A prime, so this implies, this is okay, that now if you imply that F hat is a representative of F prime, implies what? There exists A tilde in F prime such that A tilde intersection B is phi. Done. Okay. So, what it means that, look, given A, given B, if there exists an A, you know there exists an A prime. Now, you use this for the same way, now you know there exists A prime. Now, because F hat is a representative of F prime, means for every B, if there exists something in set F prime which it is disjoint with, then F hat has to respect that, which implies that I can find A tilde. So, this immediately implies right. This immediately implies that F hat is a Q representative of F. That's it. So, there is, so why did I bring this? Because look, if the F we have to always work with is this. But we will never work with such an f. We will work with an f prime, right, subset of f, okay, with the property that f prime is a Q representative of f and f prime is not too large. In fact, we will guarantee that f prime is at most some n to the power at most. So, yes, it can be big, but it is only big with respect to p plus pq, slightly larger, and every time, because we are guaranteeing this is the f prime that will feed to our algorithm and get f hat. Okay. Okay, so I think this is a good place to stop here and do the applications in the third lecture. So, in the first lecture we try to give motivation to this definition of representative families and how it is connected to two families theorem in the combinatorics, how we can use that combinatorial theorem to build up this machinery, how we can use just the normal knowledge of deheating set algorithm to compute this, to come with an algorithm or design an algorithm to compute this representative family. And in the next lecture, we will show you how this transitivity could be used to design good efficient algorithm. Okay. So, with that, we will close the second lecture.